Hi everyone, we are going to be teaching you about probability density functions today. I am David Fan.
This is Howard Bai.
And next to us is Mr. Yash Singh. This is our first time making a video and it was a lot of fun, so we're really excited to show you the video. So a brief outline of what we're going to talk about. We're first going to discuss discrete probability and compare it with continuous probability. Then we're going to formally define the probability density function and teach you guys how to find the probability for a range of possibilities using integrals. And then we're going to give you some examples for you to try. You can pause the video in case if you need time to work out the problems, and then you can just press play to see our solution. And then we're going to finish with some applications of probability density functions. Have fun! So before we discuss probability density, let's review the concept of probability. What is probability? It's simply the chance that something will occur out of a set of known possibilities. When you think about probability, the first things you might think of are flipping coins or playing rock, paper, scissors. These are examples of discrete probability, where there are an exact number of outcomes, each with a specifically defined probability. In the coin example, there are only two outcomes, heads or tails. Perhaps the chance of one head is always 1/2, and the chance of tails is always 1/2. It doesn't have to be, but in other words, the probability of a certain value for a discrete variable is exactly defined. There is no in between. You can either have this value or that value. You can represent discrete probability using a bar graph or a table since it's discontinuous.
What if instead of something like coin tosses, you're thinking about something like temperature? In this case, the variable is continuous because it can take on an infinite number of possibilities between two set values or a range. Think of the difference between Bohr's model of the atom and molecular orbital theory for you chemistry enthusiasts. The graph of a continuous probability distribution will be a continuous curve. So instead of representing probability with a table or a bar graph where the y value is probability, you have to do something with calculus. Guess what it is?
You guessed it, integration. Probability is described using an integral, or area in continuous probability distributions. Why is that? Think about what continuous probability represents. You no longer have specific, exact, defined values because they don't exist. For example, if I ask you what the chances are that tomorrow's temperature would be exactly 60 Fahrenheit, you should tell me, David, you're crazy. That's impossible. And you'd be absolutely correct. Not 60.01, not 59.9999, but exactly 60 Fahrenheit. That's impossible. You have to find the probability that it will be close to 60 or a range of possibilities, which is done by adding up lots of vertical lines, forming an area under a curve. Probability can't be thought of exact values for single points in probability density functions. Otherwise, the integral would be 0 at a particular point, since the width of the rectangle would be 0.
Let's formally define the probability density function f of x. The probability of getting a value in between a and b, both of which are defined in f of x's domain, is equal to the integral of f of x from a to b. There are two requirements for a probability density function to be valid. The integral of f of x over its entire domain must equal 1 or 100%. It is certain that something will happen out of the set of possibilities that you know exist. The other requirement for a probability density function is that f of x must be non-negative across the domain in which it is defined as a PDF. Remember these two criteria. This is important.
Okay, let's do an example. Let's say we want to find the probability that temperature tomorrow will be 33 degrees Fahrenheit or higher. Probability density function f of x is 0.025 pi sine of 0.05 times the quantity pi x minus 20 pi for the domain of 20 less than or equal to x to less than or equal to 40. It's cold in this particular place. Let's integrate f of x from 33 to 40. So the antiderivative of sine u is negative cosine u. But don't forget the chain rule factor is 0.05 pi. Divide by that factor so that it'll cancel out. Evaluate that antiderivative from 33 to 40 and you're set. You should get 0.273005 or 27.3%.
Here's a problem for you. Try proving that the function in the previous function is indeed a valid probability density function. Do you remember the requirements? If not, just rewind to that part again. So the integral of the function over the entire domain of the variable has to equal 1, and f of x has to be non-negative across that domain. Since the domain is 20 to 40 in this case, let's integrate from 20 to 40 and see if the integral equals 1. It does, and let's plug the function into the calculator. It's never negative, so we're set.
Lastly, let's talk briefly about random number generators and how you could describe the probability density function for the output. This is a problem for you to try too. First, generate a few random numbers on your calculator and see if you can make any observations. Click on Math, then PRB, then Rand. You'll notice that all the numbers are in between 0 and 1, and they are indeed random. This is continuous probability, so the probability of exactly one outcome is 0. It doesn't exist. But we can find the probability of a range. Do you know what the probability of getting a number between 0.25 and 0.5 is? It's 25%. Do you see why that is? So try to find a function whose integral from 0.25 to 0.5 is 0.25, or from 0.1 to 0.2 is 0.1, etc. Did you try y equals 1? The antiderivative of y equals 1 is y equals x, and evaluating y equals x from 0.25 to 0.5 indeed yields 0.25. Bingo! And this actually makes sense because it's random. Y equals 1 is a flat line, so the chance of anything happening should be equal. Everything is equally probable.
I lied. One more thing. Are you wondering what applications probability density functions might have? Normal distributions are an example of PDFs. They are commonly used in all fields, from bioresearch to finance to sports predictions, etc. You can use PDFs to predict the viability of a financial investment, what tomorrow's weather will be like, etc.
So that concludes our video. Hope you enjoyed it and that you'll look further into statistics. It is indeed a very interesting and useful field in almost all careers.